Great. Thank you, Professor Ding. Welcome, everybody. I am, in fact, going to continue along the line of data science and talk about statistical learning and operation management. But before I dive into the specific research, let me tell you a little bit about the type of work that we do at the Data Science Lab at MIT. The Data Science Lab at MIT brings together MIT faculty, PhD students, and a variety of companies from different industries to focus on some of the most challenging problems that these companies have by bringing together data, models, and analytics. The Data Science Lab is cross-industry. We have companies in oil and gas, retail, financial services, insurance, airline, industrial equipment, and even software companies who are part of the lab and implement some of the technologies that we develop. Finally, the Data Science Lab has global footprint with partners from North America, Europe, Asia, including the Middle East, and Latin America. A few examples of research that we have done. We started in 2012 after events like the tsunami in Japan and the flood in Thailand. A lot of effort around supply chain resiliency. Our technology was implemented by a variety of companies. The first company was the Ford Motor Company. And after that, we had a variety of companies like, for example, Schneider Electric, for example, Sigma, which is a large food manufacturing company in Europe and Latin America, and Accenture signed a big contract with MIT to scale our technology across industry. We have done work in inventory, transportation, and procurement optimization for companies like the Home Depot, Mango, which is a large Spanish fashion retailer. Again, Accenture was involved. And finally, Blue Yonder was one of our partners, and they implemented some of the technologies that we developed in this line of research. Work in the area of supply chain digitization in collaboration with companies like AB InBev, the large beer company, Zalando, which is considered the largest online fashion retailer in Europe. Work on price optimization for both online retailers and brick and mortar retailers. Our work was done in collaboration with the Groupon, who tested our algorithm. We have done work with Coppel. Coppel is a large Mexican brick and mortar retailer where our algorithm power all their pricing strategies. Oracle has implemented some of our technology. We have also done a lot of work around personalized offering for the airline and insurance companies. If you fly today from London to Paris, when you purchase your airline ticket, we are not involved. But once you purchase the airline ticket, our system kicks in. And think about what I'm saying. This is the MIT system kicking in and offering you ancillary product. They include priority boarding, car rental, hotel, and the like. And the offer that you get may be different than the offer that I will get because the system learned about our preference or the preference of people similar to us. And based on this, decide what to offer us. And the same is true with the insurance industry. And finally, work with Alibaba and IBM on online resource allocation. Today, I'm going to talk about the work research motivated by our collaboration with partner companies around personalized offerings. This a collaboration with partner companies around personalized offering pushed us to dive into the detail of statistical learning. And if you look at the literature on statistical learning, there are two main streams of work. One is online learning, and the second one is offline learning. Online learning can be described by the following statement. In online learning, you don't have any data that is available at the beginning of the process. Data is generated on the fly. And as you generate data, you try to make, again, decisions on the fly. Let me illustrate the process. A customer arrives at a platform. The platform may be Amazon platform. The platform may be the airline platform that I described earlier in my discussion about ancillary product. A platform may be healthcare platform. The platform observes the feature vector of the customer, the characteristic of the customer, and based on this, the platform makes decision. The decision may be, in the case of Amazon, what product to recommend to David. In the case of the airline, what price and ancillary product to offer a specific customer. For example, should I charge €7 for priority boarding or only €4 for priority boarding? So the next step by the platform is making a decision. Once we make a decision, we observe the reward. So I will use R to represent the reward, and the assumption is that the reward is generated by some unknown model that I will refer to as F star. This reward, of course, depend on the feature vector of the customer and the decision that we made. And I will call F star the ground truth reward function, right? This, if I know F star when a customer arrives, I know what to do. And so our objective is to design algorithms that maximize the accumulated reward, or equivalently achieve a low regret. What is the definition of regret? Regret is defined as the difference between the accumulated reward achieved by a decision maker who knows the ground truth F star and the accumulated reward achieved by our algorithm that does not know the ground truth and therefore need to learn on the fly. Right? That's online learning. Offline learning is different. In offline learning, all the data is available at the beginning of the process. This data is assumed to be IID, and I cannot generate new data on the fly. What is our problem? We assume that we have N samples of IID data. Each data point is a triplet: the feature vector, the decision, and the reward. And our objective is to design algorithm that will generate a predictive function F hat such that F hat closely approximates the ground truth F star. More specifically, our objective is to design algorithms such that with limited amount of data, we will generate a predictive function F hat such that with high probability, F hat will have low error relative to the ground truth F star. The only thing that is not well defined here is what is error. We measure informally, we measure error by looking at the average square difference between the estimated value and the actual value. More formally, this is the definition of error, and it's called MSE, mean square error. And so you can see immediately that online problems and offline problems are different. One, of course, assumes that all the data is IID and is available at the beginning. The other one generates the data on the fly. Second difference is the objective in offline is reduce, minimize the expected error. In online, the objective is minimizing regret. One important difference that we learned very quickly as we started doing the research is that there are lots and lots of very effective algorithms for offline learning, but this is not the case for online learning. As a result, the first question that we ask is whether it is possible to reduce online learning to offline learning, because if you can do that, then you can use all the available technology for offline learning to solve the online learning. And in this paper, we answer the question. We call this paper bypassing the monster. And so as I talk about the research here, I will explain what the reduction is, who is the monster, and how we can bypass the monster. The second line of research, again motivated by our collaboration with our industrial partner, is in particular is triggered by comments that many of them made. Remember, our algorithm were implemented in the airline and in the insurance industry. The airline executives that were using our analytics were intrigued by the performance. But one thing that bothers them was that when we start the algorithm, we always assume no data. And they said, we have a lot of offline data. Why you are not using the offline data to improve the performance of your learning algorithm, of the online learning algorithm? And so in the second line of research, we develop a framework that allow us to identify under what condition the offline data is not helpful, under what conditions the offline data is helpful, if it's helpful, by how much we can improve the performance of the online learning algorithm. Today, I am going to talk about the first topic, reducing online learning to offline learning. But I have papers on the first topic and on the second topic, and I'm happy to share both papers with you. So here is an outline for my talk. I'll start with motivation and the key research question, then explain what are the technical challenges in achieving our objective of reducing online learning to offline learning, talk about our contribution, show you the algorithm and the theoretical foundation that we develop for our algorithm, and then talk a little bit about our computational performance. So this algorithm that is really came out of theory was tested on a lot of real world data, and I want to report how well the analytics did. And so let me start with a brief motivation. To the audience, my suggestion is that you stop me at any point and ask questions. Otherwise, it's going to be a little bit boring for everybody for me just talking in a monotone way. So don't be shy. You can raise your hand, or you can just stop me and take a question. All right. So what are the technical challenges in this problem? And in order to identify them, I want to provide a very detailed definition of the general problem we are analyzing, what is called the general contextual Bandit model. We are going to play capital T rounds. Depending on the situation, we may know capital T or may not. Think about T as a number of customers that arrive to purchase an airline ticket, right? When customer little t arrives, we know the feature vector of the customer, and we assume that this feature vector is generated by some unknown distribution d of x. Once we observe the context vector, the feature vector, we make a decision. The decision may be price, the decision may be recommending a book, the decision may be personalized medicine. And we will assume that there are k possible decisions to choose from. So we made a decision, we make a decision, and then we observe our reward. And the only assumption I'm going to make is that the expected reward condition on the feature vector x and the decision that we took a is f star, which is our ground truth. And our assumption is that the ground truth belong to some class of function big F. And our objective is to minimize regret. The class of function big F may be basically anything. Can be a linear class, perhaps high dimensional linear, maybe non-parametric, maybe regression tree. If you have done data science work, you may think about neural network. Any one of them can be generating the function f star. Now, why this problem has attracted so much attention in the literature? Because it combines statistical learning and decisions under uncertainty. More specifically, this contextual Bandit problem that I just described has two important features. The first feature is what is called partial feedback or Bandit feedback. For each context, when a customer arrives, we observe the context, we can observe the reward associated with the decision that we played. We don't know what the reward will be under different decisions. And as a result, the decision maker need to use what is called the trade-off between exploration and exploitation. Exploration is trying different possible decisions. Exploitation, if I believe that something is effective, maybe focus on this strategy. The second challenge is what is called heterogeneity. What is heterogeneity? The effectiveness of each action depends on the context, but the context space is enormous, is huge. As a result, we need to somehow transfer learn. We need to propagate information across different contexts. And it's not clear that we can do this very effectively. Because of the two characteristics of this problem that I mentioned, many algorithms have been developed for this problem, from what is called, what are called upper confidence bound, UCB, to Thompson sampling. Just as a comment, Thompson sampling was developed, initial idea was in the early 1930s, and it was developed for clinical trials, and since then it has been proven to be enormously effective and interesting from a theoretical point of view. Exponential weighting algorithm, oracle-based algorithm, and many more. And the reason for this explosion of papers on algorithm is because there are many algorithms, and in fact, many applications. And in fact, people have applied these types of technology for recommendation systems, for ride-sharing platform. I applied it together with two of my PhD students, Chris Ferreira, who is now on the faculty at Harvard, and He Wang, who is now on the faculty at Georgia Tech, for dynamic pricing problems, healthcare applications. So you can see very different types of application, but the same technology, same type of algorithm have been proven effective for the various applications. This is clearly relevant to our community. community interested in operation and operation management. Take two examples. One is product recommendation. I have K product. Customer arrive one after another. When a customer arrive, I observe the feature vector of the customer, and then I make a decision, A, T, which is which product to recommend to the customer, and then I observe how the customer respond, and the customer respond by maybe purchasing or not purchasing the product. Another example is personalized medicine. You have K treatment. Patient arrive one after another. When a patient arrives, you observe the characteristic of the customer, and then you decide what personalized treatment to give the customer based on his or her feature vector. And then you observe the reward, and the assumption is that the effectiveness or efficacy of the treatment is unknown to the decision maker, something that she needs to learn on the fly. Now, what we are interested is solving the contextual bandit problem when the ground truth belong to a general function class, and we don't want to limit ourselves to what function class is. You decide, oh, the function class is linear, that's it. Or you decide the function class is more general, maybe parametric or non-parametric class. There are two issues that you need to address. One is a statistical challenge. For every function class F, we want to design algorithms that always find the optimal regret. Does this make sense? Always minimize the regret, which means that it always maximizes the total revenue. And the second one is a computational challenge. We want to make sure that our algorithm is computationally efficient. Later on, I'm going to define exactly what computational efficiency means, but intuitively, it's quite clear. If you look at the existing algorithms for the contextual bandit, you can see that the algorithms are either statistically efficient or computationally efficient, but not both. For example, if you're familiar with UCB and Thompson sampling, these algorithms are computationally efficient, but they guarantee optimal regret only for special parametric classes. If you're familiar with exponential weighting or elimination-based method, this algorithm always guarantee the optimal regret, but they are computationally completely inefficient. So what is the research question that we are focusing on? And let me describe it very in detail. So suppose you are given a general function class F. All the statistical and computational aspects of offline regression are well known. That is to say, if we have IID offline data, we know how to find a predictor F hat such that F hat achieves the lowest estimation error, and it can be executed efficiently. So for offline, we have lots and lots of tools that allow us to do that. The question is, at a high level, can we reduce a general contextual bandit to the general offline? And the intuition, if you can do that, you can use what's available for offline to solve the online. More specifically, here is our question. Given a class of function F and an offline regression oracle like least square or variation of least square like Ridge and Lasso or any other offline regression oracle, is it possible to design an algorithm for the contextual bandit problem such that this algorithm always achieves the optimal regret whenever the offline regression attains the optimal or the minimal estimation error, right? Whenever the offline is great, the online should always be great, should also be great. Second requirement is that this algorithm that we are designing should require no more computation than just making a few calls to the offline regression oracle, right? So when we did our work with airline and with the insurance, I talked to a lot of CS people, and the underlying assumption was this problem, lots and lots of very smart people have looked at. And in fact, this problem is mentioned in many, many papers. And the underlying assumption is this is impossible. In general, it is impossible to reduce the general online to the offline so that we can use the offline technique to solve the online problem. Surprisingly, what I will show you here, we prove that there is a very simple algorithm that achieves that objective. Meaning, if you have an efficient offline algorithm, we can transfer the online problem into an offline, use whatever you have to solve the online problem. And so before I show you the algorithm, let me try to explain why this is technically very difficult and why the intuition of most CS people was that it's impossible to find such an algorithm. And in fact, there are really two, there are more, but at the heart of the problem, there are two statistical challenges. One associated with confidence bound and one associated with dependent action. Let me explain each one. If you look at UCB, upper confidence bound algorithm, or Thompson sampling, they work only for certain parametric model. And the way they work is by generating confidence bound for every pair of feature X and decision A. But we know from statistics that it's impossible to do that for general function class F. And indeed, Foster and his co-author in 2018 proposed a computationally efficient confidence-bound algorithm that applies, that use offline regression oracle. So this is exactly what we are trying to do. But because they are focusing on building confidence, confidence-bound, they can show that they generate the optimal regret only under very strong assumption on the function class, on the distribution model. But in general, they do not necessarily guarantee the optimal regret. So their algorithm is computationally efficient, but not statistically efficient. The second challenge is a challenge associated with analyzing dependent action. If you think about the offline learning problem that I mentioned, offline learning assume data is IID, right? That's the starting point of any offline problem. But online data is nothing but IID, because the decision that I make today based on all the data that I have observed until today. And so there is direct relationship between what I am deciding now and what I have done before and what I have observed before. So we cannot assume in the online learning that the data is IID. For that reason, that data in online learning are not IID, Dylan Foster and Sasha Racklin, Sasha is on the faculty at MIT, actually he's a colleague of mine in the CS department. Dylan Foster was his postdoc, now he works for Microsoft Research in New England. Because of this reason, they develop an optimal and efficient algorithm for the general problems that I'm looking at, by assuming that they have access to online regression oracle, right? So the beauty of using online regression oracle, we are trying to use offline. But the beauty of using online regression oracle is that it provides statistical guarantee for any data, even if it's adversary. So the fact that the data is not ID, they don't care about, right? It's still, they can tell you what are the statistical guarantees. The problem is that we have computationally efficient algorithm for the required online regression oracle only for special function classes, not for anyone. And we want, you give me a function class, I want to show you an efficient algorithm. So here is our contribution. We provide the very first optimal and efficient black box reduction from the general contextual bandit to offline regression. Our algorithm, as I will show, is very simple. It's extremely fast. Our ideas build on two lines of research in the contextual bandit. One starts with a very old paper by Abe and Long, where they introduce what they call sampling algorithm or randomized algorithm. And in effect, Dylan Foster and Sasha Ackling build their online regression oracle using the idea from Abe and Long. And then a completely different line of research by Agrawal, who is not focusing on the function class space, but is analyzing problem in the policy space. We basically show that these two lines of research are tightly connected. Our analysis is different than the analysis in these papers, but the bottom line is that it allows us to show that any advance in offline regression translate into the contextual bandit both statistically and computationally. To put our results in perspective, let me show you and mention some of the algorithms that exist in the literature. One of the first, not the first, but one of the first algorithm for the contextual bandit is regression elimination that always guarantee to find the optimal regret, but it's computationally intractable. In 2014, Agrawal and his co-authors came with an algorithm that guaranteed to find the optimal regret by making few calls to offline classification oracle. Offline classification requires solving NPR problem. So this is statistically efficient, but computationally not efficient. RegCB is, I mentioned Foster 2018 earlier. RegCB makes polynomial number of calls to offline regression oracle, exactly what we are looking for, but it's suboptimal. It guarantees to find the optimal regret only in special cases. SquareCB is the algorithm from Foster and Racklin, guaranteed to find the optimal regret by making linear number of calls to online regression. The problem here is that efficient algorithm for online regression exists only for very simple function classes F. In general, we don't have efficient algorithm. Our algorithm, which I call Falcon, always guaranteed to find the optimal regret by making log T calls to an offline regression oracle when T is unknown in advance. And if T is known, we can reduce the number of calls. And the algorithm is computationally efficient because it's really making just a few calls to the offline regression problem. So whatever you can do in the offline, I'm going to use it in the online. Remember, the title of our paper is Bypassing the Monster. Where is the monster name coming from and what does it refer to? In the CS literature, in the contextual bandit literature, monster refer to algorithms that requires enormous amount of computation. The first people to refer to their own paper as the monster paper are Dudik and his co-authors. They develop an algorithm for the same problems that I'm describing that guarantee to find the optimal regret, but they said about their algorithm, the algorithm requires a monster amount of computation. That's why they call the paper the monster paper. The AgriWell 2014 paper present actually a fast and simple algorithm for the contextual Bandit problem by calling offline classification oracles. The only problem here is that you need to solve NP-hard problem and you need to solve a multiple NP-hard problem. That's why they call their paper, they title the paper Taming the Monster. We are completely bypassing the monster by just assuming that the ground truth belong to any class of function f. You give me the class, I show you the algorithm for this problem. So what is the algorithm that we have developed? The algorithm has three components. One is what I call epoch schedule. What is the epoch schedule? We subdivide the time interval into sub-intervals of increasing length, right? I'll show you how we subdivide in a second. Then at the beginning of every sub-interval, we make a single call to the offline regression oracle, and we obtain a predictive function f hat. But we are not going to use the predictive function f hat in a greedy fashion, because if we use it in a greedy function, it's possible that the predictive function is not correctly represent the ground truth. Therefore, we will move in the wrong way. As a result, what we are going to do is to use a sampling rule. Think about sampling rule as a randomized algorithm. We call this algorithm Falcon for fast, least square regression oracle for the contextual Bandit, and the name is after this animal. So let me explain each one of the steps. The first one is the epoch schedule. We are going to take the time interval and divide it into sub-intervals. If we don't know how many customers arrive, then we use just a geometric sequence, which means that the number of sub-intervals will be log t, and the length of the sub-intervals are going as we move from epoch to epoch. If we know t, then we can reduce the number of sub-intervals to log of t. Notice that because the length of the sub-interval is increasing, as we move across time, we are going to call the oracle less and less frequently, because we call the oracle at the beginning of each sub-interval only one time. Now, at the beginning of epoch m, right, when we are at the beginning of interval, sub-interval m, we call our least square oracle, if that's the one that we are using for offline regression, to obtain a predictor f hat. If we like other offline regression, we use whatever the offline regression that we prefer to use. It can be, as I mentioned, Ridge, Lasso, or anything else. Now, once we have f hat, it is tempting to say, given the predictor f hat, I'm going to use for every context the greedy action, the one that maximize the reward according to f hat. The problem is that f hat may not be the ground truth, and so I need to perform some exploration, and that's the idea behind the randomized algorithm, and you can see it here. Our randomized algorithm starts with identifying what I call a learning rate, gamma m. So at the beginning of epoch m, we define a learning rate. You will see the role of the learning rate in a second. But the point is, as we move from epoch to epoch, the learning rate increases. Now, suppose customer little t arrive in epoch m. we know the context vector of the customer, the feature vector of the customer. We already generated a predictive function f hat, and so we can determine the greedy action. Simply just the best action that will maximize reward if f hat was true. But we are not necessarily going to use the greedy action. We are going to decide a non-greedy action A with probability inversely proportional to the difference between the predictor that we have f hat under the greedy action and the predictor under action A. The higher this gap, the lower the probability. So think about this as an exploration step. We are testing non-greedy action. And with the remaining probability, we are going with the greedy action. So this is exploitation. Notice that what control the probability of selecting a non-greedy action is the learning rate. And you observe that as we move from epoch to epoch, the learning rate increases. As a result, the probability of selecting non-greedy action decreases. Why? Because we feel more and more confident about what we have learned. What can we say about the algorithm? We prove the following, that when the function class big F is finite, our algorithm guarantee an expected regret of no more than a constant times square root of kt log of f. As we mentioned, using log t call to a least square regression or call when t is unknown. If t is known, we can reduce it. The beauty of this result is that there is a matching lower bound. So we know our algorithm in this case achieve always the optimal regret. And we only require log t calls to the least square regression oracle. What about general function class? So let me set up the environment. Suppose for a given NIID samples, right, we have an offline regression oracle, whatever it is, that return an estimator f such that the estimation error is bounded by ER, right? This is our estimation error. ER is our estimation error guarantee, right? And it's clearly dependent on the sample size and the function class. The higher the sample size, the lower the error. We prove the following. Given such an offline regression oracle generating an estimation error guarantee ER, our algorithm guarantee an expected regret no more than a constant times square root of k, ER times t, following the standard statement that says if you don't know t, log t call. And the beauty of this is that we know when the offline regression oracle generate the minimum estimation error, that is when ER is the minimum estimation error, this is also a lower bound, which means that when the offline is optimal, our algorithm is optimal. Does this make sense? So the algorithm has a simple structure, guaranteed to find the optimal regret when the offline oracle find the minimum estimation error, just by making a few calls, in fact, no more than log t calls to the offline regression oracle. Now, we can apply the theoretical result to improve on existing results in the literature. So, if f is a linear class of function with dimension d, we know that least square ensure an error proportional to d over n. Our algorithm immediately imply a regret or proportional to square root of kt times d plus log t, and this is the best known now. It improves on what's known in the literature as a function of t. When f is linear with dimension d and sparsity s, Lasso ensures that the estimation error is proportional to s which is a sparsity, log D divided by N, our result implies that the algorithm guarantee a regret proportional to square root of Ks T times log T. You can apply to neural network, you can apply to other cases. So the result is very general. And we don't have a lot of time, but I want to skip the proof sketch and show you just some computational results. And the computational results, if Professor Ding, I can get 3 more minutes, I'll show you quickly some computational results on real-world classification problem, recommendation systems, and price optimization. So first, we took data, real-world data for classification and recommendation problem, 10 classification problems and 2 recommendation problems for Microsoft and Yahoo open source datasets. Just for those who are not familiar with classification is really a fundamental task in machine learning. It's used for recognizing handwriting, for face recognition, for identifying customer segments, for promotion. So the application is everywhere. And by the way, when I'm going to test our algorithm, if our algorithm classify a customer correctly, then we have no loss, 0 loss. If we make a mistake, no matter what the mistake is, we have a unit loss. Recommendation systems are also, in effect, everywhere. They try to predict the ranking or the ratings that we will give, that the user will give a specific product. Customer arrive to the system want to recommend a product that she likes. If we recommend a product that the customer ranked high, then we have small loss, otherwise large loss. And these kind of systems are used by Amazon, Netflix, Google. You think about online platform, you see that they are using them. And we finally, just a comment, we compared our algorithm against 8 existing algorithms for online learning. All are in open source library called VW. The version, we applied our algorithm about 6 months ago. So at that time, the most up-to-date version was version 8.8. What are the 8 algorithms? One is greedy, just use a greedy action. Epsilon greedy is similar in philosophy to our algorithm without the epoch and without the specific tailoring of the algorithm. It means use greedy algorithm with some probability and uniform select across all the other action. 2 versions from the paper, Taming the Monster. 2 versions of Thomson sampling, and the best algorithm until our algorithm was published come from the paper by Foster and his co-author in 2018. One version is RecCB elimination, the other one RecCB optimistic. So I will stop after explaining this slide. So what I'm doing here, I'm using what is called win-loss difference across the 12 data sets. Remember, 12 data sets include ranking and classification problems. Inside, if you see my pointer, inside you have the 8 different algorithms, and in the inside inner table, I'm comparing each of the 8 algorithms against the other 7, right? On the 12 data sets. So for example, take bag greedy versus greedy. On the 12 data set, suppose bag greedy won statistically significant performance on 6 problems out of the 12. On 2, greedy statistically outperform bag greedy. On the rest, it's hard for us to say. Then we record 6 minus, minus 2, which is 4. You can see that RegCB, either elimination or optimistic, are doing very well. In fact, optimistic is the best, right? It never loses to anybody. Now, we tested 3 versions of our algorithm because we can assume whatever we want on the class of function big F. So the first version is assuming big F is linear and applying least square estimator. The second is assuming the big F is linear and applying ridge estimator. And the third, assume a general function class F, like regression tree, and using gradient boosting. And you can see our algorithm did very well. And the most general one, which is Falcon 3, never loses. In fact, outperform everybody on all the data sets. Let me, we have also tested it against on pricing data, and the algorithm performed very well, but I'll stop here.